Duncan, and Jessie Duncan is a NASA postdoctoral program fellow at Goddard Space Flight Center, working on high-energy observations of the solar corona. She received her PhD in physics from the University of Minnesota in 2022, and in her career she worked on several topics, among which solar microflares, coordinated observations with NuSTAR and other observatories, and development of hard X-ray detectors for solar applications. And today she'll give us a talk about understanding the hot solar corona via X-ray observations with NuSTAR. Jessie, go ahead.
All right, thank you very much for the introduction. So today I'm going to be talking about using NuSTAR to look at the sun. This first slide has a photo of, or a visualization of NuSTAR, as well as a composite image of the solar disk, which is taken in several wave bands, extreme ultraviolet in red, soft X-ray in green, and hard X-ray with NuSTAR in blue, showing the relative temperatures of different parts of the solar disk during one of our observations. So I'll get right into it. Maybe. No, we went through this. Oh, okay, now it works. So to start out, I will give a brief overview of the solar corona because I know that this is not a solar physics crowd specifically. The corona is the outermost layer of the solar atmosphere. You can actually see the corona by eye during a total solar eclipse. The photo on the right-hand side of the slide shows the white light corona viewed during the 2017 Great American Eclipse. And I'll just do a little pitch. There's going to be another total solar eclipse this year in America on April 8th. So if you have the opportunity to drive into the path of totality, I would highly recommend it. It's a really amazing experience. And you will actually be able to see the corona with your bare eyes. So the corona is very hot, more than 1 million degrees in comparison to the around 6,000 Kelvin photosphere or surface of the sun. And I'll talk a little bit more about that temperature difference later. The corona has fairly low density in comparison to other parts of the solar atmosphere, and its dynamics are defined by the magnetic field. It's a low beta plasma. There are active regions within the solar corona, which consist of elevated magnetic activity in comparison to sort of the rest of the corona. These occur when magnetic flux emerges from lower down in the sun and creates sort of loop structures that extend higher up into the corona. There's a cartoon of this on the lower left-hand side of the slide showing you basically how loops can have their foot points rooted to lower down in the solar atmosphere, but will have sort of the loop tops extend upward into the corona. And a consequence of this is that convective motions lower down in the sun can torque the loops that extend up into the corona, which can lead over time to a buildup of magnetic stress. This in general means that active regions are hotter than the rest of the corona, often observed at a average temperature of 2 or 3 million Kelvin in comparison to the 1 million sort of quiet coronal temperature. Additionally, we will often see the magnetic field relaxing to a lower potential state via magnetic reconnection. And in these transient events, energy is transformed from the magnetic field into other forms. So these events are flares, jets, coronal mass ejections, other forms of solar transients. And in this case, we have rapid heating, generation of plasma waves, bulk motion of material, and particle acceleration. And in these transients, like especially in solar flares, we can reach even higher temperatures of up to 10 million Kelvin, or sometimes even higher than that in the larger flares, up to perhaps 20 or 30. So why X-ray observation? This is because both hot plasma and accelerated particle distributions in the corona will emit in the hard X-ray range. And when I say hard X-ray in this context, I'm specifically talking about the range above about 3 or 4 keV. That's not an exact definition, and where the soft X-ray and hard X-ray is divided will sort of depend on who you ask, but that'll be the definition I'm working with here. So both non-thermal particle distributions and hot plasma will be emitting in this range when they're coming from the corona. In the non-thermal case, this is the result of X-rays from accelerated particles interacting with the ambient plasma. So because we can get direct Bremsstrahlung emission from those interactions in the X-ray range. This is an excellent diagnostic of acceleration processes and how they are affecting the development of transients. Thermal Bremsstrahlung, on the other hand, is Bremsstrahlung just from the thermal motion of the plasma, which can extend up into the X-ray range for very hot plasma in the millions of Kelvin. And observing the thermal distribution in X-rays can allow us to understand the distribution in terms of temperature and how it evolves in time, which in turn can help us understand how heating is proceeding in the corona. There are 3 solar-capable hard X-ray instruments that I'm going to highlight today. On the far left, there we have RESI, which is sort of the most fundamentally defining instrument in terms of the sort of progress of understanding the corona and understanding specifically solar flares in the past few decades. RESI observed for over 16 years. It was a heliophysics SMEX mission. It observed both in the X-ray as well as up into the gamma ray range, and it was designed and optimized to look at large solar flares and understand the process of particle acceleration and other forms of energy release in these extremely large, bright events. Because of that, though, it had fairly limited sensitivity as its indirect imaging method was not optimized to be sensitive to very faint X-ray sources in the corona. A more sensitive type of instrument is an instrument that directly focuses X-ray light, because this allows a much smaller detector volume and therefore a lower background. And the FOXY rocket program, which is the middle instrument on this slide, has been working for a few decades to develop this type of instrument for a solar-specific context. It's much more sensitive than RESI was and improves over RESI also in dynamic range and effective area. But we only have had 3 5-minute rocket flights so far with FOXY. A 4th one is scheduled a little bit over more than a month from now in the beginning of April. But in the meantime, we want to get more observing time with sensitive focused X-ray observation. And so we have also been using NuSTAR to observe the sun. NuSTAR is an astrophysics mission that I'm sure many of you are very familiar with. It can actually also look at the sun. We've had observations a few times a year since 2014 via the guest observer program, as well as other directors' discretionary time and other sort of similar situations. NuSTAR has extremely high sensitivity, much more sensitive than RESI, because it's designed to look at very faint astrophysical sources very far away. Some of its weaknesses, though, that are sort of specific to the solar context include the fact that its detectors were not optimized for the really high flux that we see from the sun. So we have to be careful about what sources we observe on the sun with NuSTAR. It's not able to observe large flares. It's really better for sort of smaller magnitude events. There are also some issues with ghost rays and not the highest angular resolution, but we can still do a lot of really interesting science in the solar case of NuSTAR, which I'll talk about a little bit on the next slide. So some ideal NuSTAR solar science targets. Basically, this is any sort of situation in which the corona is not as particularly active. So the faintest, I guess, X-ray emission that we ever see from the corona would be the X-rays from the quiet corona. So this is not only when no large flares are happening, but also in a situation where there are no active regions currently present on the solar disk. And so this has allowed us to, for the first time ever, get a full understanding of the X-ray emission from the quiet corona. You can see a sort of NuSTAR mosaic style image of the quiet corona from the Patterson et al. 2023 paper. And so this is a new capability that was enabled by doing NuSTAR solar observation. So far, we have not found evidence for non-thermal accelerated particles in the quiet corona, but we want to continue to build our statistics in observing the quiet corona as we continue to make these observations over time. We also can observe active regions at quiescent times, so when they're not flaring. And I'll talk a lot more about that in sort of the latter part of this presentation. And we can also observe microflares, or we can also observe active regions when they are flaring, but it's just little tiny flares. So microflares are, as the name suggests, flares that are around 10 to the 6 times fainter than the brightest flares that ever occur on the sun. And you can sort of see in this plot here, which is showing flare brightness versus sort of spectral shape as for all X-ray transients that have ever been observed on the sun, or at least all observed with the instruments I've been talking about today. RESI is this sort of reddish heat map towards the top left-hand side of this plot, and that's the distribution of all RESI flares observed over their 16 years of continual observation of the sun. And then everything else on the plot is individual X-ray microflares observed by NuSTAR and FOXy, and you can see that we are investigating a totally new range in terms of the magnitude of these events. We're able to characterize how energy is released in much smaller transients than was ever possible before. So moving on, I'm now going to talk specifically about quiescent active regions and one of the fundamental science questions that we can investigate when we do NuSTAR solar observation. And this is, what heats the solar corona? So as I mentioned, the corona is very hot. Particularly, it's a lot hotter than the photosphere or surface of the sun. So looking at the plot on the right-hand side of this slide, you can see the temperature of the solar atmosphere and the density of the solar atmosphere shown as a function of height above the photosphere. And as we move from left to right, we see that the minimum temperature of the solar atmosphere occurs in the photosphere, and then it continues to rise afterward, especially in the transition region, a narrow region between two parts of the solar atmosphere called the chromosphere and the corona, where we see a really rapid increase in the temperature. We understand from basic thermodynamics that we cannot have direct flow of heat from the hot core of the sun out to the corona, because you can't have it pass from the cooler photosphere to the hotter corona. And we know energetically that this energy must come from the magnetic field, but we're not sure exactly how. The observed solar flare population, which I've briefly discussed, the flares that we observe across a wide range of scales that we can individually resolve do not provide enough energy. Several statistical studies over the past few decades have examined the flare frequency distribution and shown that there's not sufficient energy to explain the elevated temperature of the corona. So there are a couple of theories as to what can provide an explanation. One is a sort of reconnection-based or flare-like type of event called nanoflares, which was put forward by Eugene Parker, the namesake of the Parker Solar Probe. This would basically, the idea here would basically be that there are many flares happening that are of such faint magnitude that they would be completely unresolvable, involving elementary loop structures happening all over the corona all at once. And we'd be able to examine their combined effect, but not actually individually resolve them. But it's also possible that the corona is heated via other mechanisms, such as the dissipation of MHD waves. And one diagnostic that we can use to distinguish between nanoflares and other heating scenarios is to look at the thermal plasma distribution as a function of temperature. This is because a nanoflare-like scenario is expected to have a lower frequency of individual heating events, which in turn means that the plasma distribution should be broader, whereas a wave heating-like scenario would have a higher frequency of heating and therefore a thermal distribution that is peaked narrowly around the average temperature. So we particularly want to look for really hot material, more than 5 or more than 10 million Kelvin, present at times where there are no obvious flare-like transients happening. And because this is a direct sign of low frequency heating. It's not possible for those temperatures to arise in a high frequency heating scenario. So in order to do that, we want to constrain the thermal plasma distribution. And to do this, we need to make observations of active regions with a number of different instruments, because different instruments we have are sensitive to different parts of the thermal distribution. The method that we are going to use to do this is differential emission measure, or DEM inversion, which basically allows us to estimate the line of sight emission measure, which you can think of qualitatively kind of as just how much material there is as a function of temperature. And this plot shows constraints on the possible thermal distribution of a single quiescent active region that we've observed. The sort of fall colored constraints labeled with an A in the key here are all different channels from the AIA Extreme Ultraviolet Observatory. The blue curves are from Henoday XRT soft X-ray diagnostics, and the purple curves are from the NuSTAR hard X-ray energy ranges. And you can see that particularly on the high side of the thermal plasma distribution with the highest temperatures, the overwhelmingly strongest constraint is provided by the NuSTAR hard X-ray observations. And this is because these high energy observations are uniquely sensitive to the very hottest material. However, even though this is a really powerful diagnostic to properly constrain the hottest temperature material, DEMs that have used hard X-ray emission are so far fairly limited in the literature, which has largely been an issue of observational constraints. And so here I'm talking specifically about doing DEMs of hard X-ray of quiescent active regions. And of course, with RESI, we're not particularly sensitive. So there was only ever one quiescent active region DEM study, and this was a DEM study of a particularly anomalously bright active region, because it had to be in order for RESI to actually be able to image it. There have also been a couple of quiescent active region studies with Foxy rockets, but this is very constrained in terms of the amount of observation time that we have. So there were two. But to get a little bit more coverage and time, we want to use NuSTAR to do this, which is great because it's highly sensitive and can observe regions when they are quiescent. So getting this process started of doing DEM studies of quiescent active regions in order to understand the heating mechanisms that might be explaining their plasma distribution has been work I've been involved in the past couple years. And so this is the slide comparing results from NuSTAR to results from one of the Foxy quiescent DEMs. So this in the top left corner is an image from Ishikawa et al. 2017, and this was a Foxy 2 and XRT DEM of an active region observed in 2014. And they found a lot of material above 10 million Kelvin, even though there was no flare happening. And the conclusion of that paper was that it was best explained by low frequency heating. So it's been hailed as a direct detection of nanoflares. In contrast, when we have done DEMs of a region that we observed with NuSTAR, XRT, and AIA in 2018, we have a little bit more observing time, and we have looked at this region as a function of time over about 5 hours of observation time during a 7-hour window. So the plot on the bottom is showing the total amount of plasma above certain thresholds, 5 million, 7 million, and 10 million in pink. As it evolves over the course of our observation of the active region. You can see sort of transients during this observation, which are microflares occurring. And you can also see some time when the time profile of the amount of plasma above these certain thresholds looks sort of flatter. Those are quiescent times. And comparing the pink curve that we have from this DEM analysis to sort of the darker red bar across the bottom plot, that is the 95% confidence interval from the Ishikawa paper. So we can see that at quiescent times, we are observing several orders of magnitude less material above 10 million Kelvin in this active region than was observed in that prior region. So to say that another way, we have at this point a sample size of 2 in terms of what regions we've been able to characterize with this sensitive hard X-ray observation in order to get a sense of the thermal distribution. And we're finding very different thermal distributions at the high temperatures in these 2 regions, suggesting that these 2 regions are heated by different mechanisms. So what's next? Obviously, having a sample size of 2 with 2 very different conclusions from each is a strong motivator to look at more regions. So there are about 100 hours of candidate quiet and/or microflaring NuSTAR observations that have ever been made of the solar corona. This has been in progress since 2014. So the next immediate step will be to do more of a statistical study where we look at all of these and examine how the plasma distribution looks at each time and can start perhaps correlating the type of distribution that we see to other properties of the active region, or anything else that might be interesting. But ideally, we would like to have a solar optimized, solar dedicated focused hard X-ray telescope that would be observing all the time rather than just on a rocket flight every few years. There's an upcoming MIDEX concept called FIERCE that will be able to do this. And additionally, would be able to do a lot of great flare science. So that's, I think, all I have today. Keep an eye out for our work Duncan et al. 2024, which gets into a lot more detail about the thermal distribution of this active region and how it evolves. That's currently in revision, and I would be happy to take any questions if people have them.
Thanks for the nice talk. Any questions?
Those microflares look very interesting. They all appear to be surprisingly similar, about a factor of 10 in amplitude, if I read the plot correctly. I would have thought there might be, bigger ones, smaller ones, but it didn't look that way in your lectures.
Yeah, so this is about I think on this plot maybe there's maybe 23 total events. So firstly I would say that doing a much broader study will definitely allow us to sort of expand our sample size here. We're seeing a difference in a couple of orders of magnitude in brightness, or equivalently with flares we talk about the GOES class, which is sort of like essentially also the brightness. But yeah, the thing that is sort of striking about this plot though is that here we're showing a relationship between kind of a ratio between the flux at two different energies versus just the flux at one energy. So it's like a brightness versus hardness diagram, basically comparing the spectral shape as a function of brightness. And that's sort of what this plot was designed to show, is that there seems to be like a pretty clear relationship where as the magnitude of the event increases, the sort of spectral hardness increases as well. So basically the larger events are likely to be hotter and or more non-thermal.
The Silich paper that you had a reference to emphasized the time-dependent ionization, and the fact that the continuum will show you the hot gas, whereas AIA might not. Have you made any comparison with the AIA in the regions you looked at?
Sorry, I didn't quite catch the beginning of that question. Were we talking about this plot?
Well, for instance, yeah, but that's an equilibrium plot. But in ionization, in a microflare, the gas will not be in ionization equilibrium.
Mm-hmm.
That was what was the point of the Klimchuk paper that there was a reference to at one point.
Mm-hmm.
The AIA will not show you the high temperature lines, whereas
Yeah.
Well, so I was wondering if you've made a comparison specifically with the AIA observations in those regions you looked at with NuSTAR.
Yeah, so for the differential emission meta analysis of this region, I have comparisons of doing the DEM just with AIA versus doing the DEM with the higher energy instruments included as well. And it's definitely important to have the NuSTAR constraints at the high temperatures, both because it's just a lot more sensitive of a diagnostic in comparison to the high temperature sensitivity of AIA, but also because we're mostly observing the continuum with NuSTAR, so we're not as sensitive to those non-equilibrium ionization effects that could affect spectral line observations. This also really comes into play when we compare instruments like NuSTAR to instruments that could do soft X-ray line observations, because that can be a really great diagnostic of high temperature material as well, like really hot spectral lines. But again, as you said, when you have a transient, we may not be in ionization equilibrium. So observing the continuum in hard X-ray can be a really powerful diagnostic there. Yeah. And the possibility of combining soft X-ray spectrally line diagnostics with continuum diagnostics in the hard X-ray would be really interesting, because that could actually serve as a direct probe of the ionization state, like looking at the difference in sensitivity between these two diagnostics.
Oh, sure. You probably implied this, but do you know the rate of the microflares, maybe from monitoring with NuSTARs? And then you can add up the total luminosity in that. And is that still far short of what you need to heat the corona?
I would say, so we have not been able to do a statistical study of the very faintest microflares because we've only been able to observe a few times a year with NuSTAR, and we haven't been able to, we also don't have the ability to make observations as well towards solar maximum, which because we get a lot of ghost ray contamination from other active regions. But the statistical studies done with other instruments, such as with like RESI's microflares coverage, suggested that it's not sufficient. And I don't think that we are seeing strong evidence that to counteract that necessarily. But yeah, it would be great to be able to have statistical continuous coverage of the very faintest little transients as well.
There's one final question from the chat online, and is does the overall solar activity level affect the efficiency of the different heating mechanisms?
Yeah, we would love to know that. Yeah, I would love to be able to start looking at, so, you know, I mentioned that we have about 100 hours to look at, and things, using this method, we can clarify which heating mechanisms are likely present in different regions. And so I would love to start being able to correlate that with things like the magnetic structure of the active region. There are sort of a lot of different sort of topologies that we see in active regions, how long an active region has been around, the solar cycle, how long it's been since the last large flare. You know, there's any number of really interesting properties that we can look at once we start to have a larger catalog of regions that have been analyzed in this way.
Okay, excellent. We have to move on. So let's thank our speaker again. And please stay online and enjoy the next talk, which will be by Emily Silich. Emily is a third-year graduate student and NSF GRFP, oh my god, sorry, fellow at Caltech, and she will be visiting the CfA as a postdoctoral fellow for the next year. Her work focuses on characterizing galaxy clusters mergers through observation and simulations. And here at CfA, Emily will be working with John Zuhon on CGM simulations. And today she will give us a talk about ICM-SHOX, improved constraints on mergers with Sunil Zeldovich, hydrodynamical simulation, optical, and X-rays. The more the merrier. The more the merrier it goes. So go ahead.
Great. Firstly, Andrea, would you like to help me get rid of this?
Is your mouse off? Oh. Sometimes we have to exit first. There's no mouse.
The mouse has disappeared.
Sorry.
We're working on it.
Yeah, no, I know, but I'm trying to, there we go, double exit. Let's close this. No, it's fine. Okay, where's it? Play. This will hopefully go away in a minute. Wait, more. Okay, but the mouse is gone again, so let's just do more.
Yeah, this guy.
Here it is, hide floating meeting control. Play. Okay.
Okay, awesome. Sorry about that. Yeah, so thanks for the introduction. I'm Emily, and I'm going to be talking about the work that I've been doing the first couple of years of my PhD with all of the collaborators listed here. So as a bit of introduction, major mergers between massive clusters of galaxies are one of the primary growth mechanisms of galaxy clusters. And so they're really interesting both astrophysically and cosmologically. So these mergers are extremely energetic events, and so they can drive bulk motions and turbulence in the ICM with velocities up to several thousand kilometers per second. They can also heat that same gas up to temperatures of 10 to the 7, 10 to the 8 Kelvin, and they can start to drive really interesting spatial offsets and velocity decouplings between the dark matter and the baryon distributions in these clusters. So think something like the bullet cluster here. And so astrophysically, clusters are really useful so we can understand how ubiquitous physical processes, things like turbulence, accretion, and shocks, in the really extreme cluster environment can influence cosmological structure formation. And they also allow us to probe cosmology because we can compare observationally derived population statistics of merger parameters to population statistics which are predicted by cosmological simulations. So we can use them to probe lambda CDM. And so there's a host of studies of galaxy cluster mergers in the literature, but generally these analyses are primarily limited in one of two ways. So firstly, previous analyses only tend to involve a single object because of the need for really deep multi-wavelength data in order to adequately characterize a merger. And then secondly, most of these analyses focus on mergers occurring in or near the plane of the sky, so that your merger morphology features can be really straightforwardly interpreted and you can more easily infer merger parameters. And so our project, ICM-SHOX, attempts to overcome both of these previous limitations. So our acronym stands for Improved Constraints on Mergers with SC, Hydrosims, Optical, and X-ray. And basically, ICM-SHOX comprises an 8-cluster sample and an associated analysis pipeline that allows us to compare cluster observables to mock observables derived from hydrodynamical simulations in order to infer merger parameters. So we've compiled a uniform sample of multi-wavelength data for a set of 8 galaxy clusters. These are extremely massive galaxy clusters at intermediate redshifts from about 0.25 to 0.6. And the really important thing here is that they span a wide range of dynamical states. So we have 3 clusters, which are presumed mergers likely occurring in the plane of the sky. 4 of these clusters are presumed mergers likely occurring in or near the line of sight. And one of them, Able 1835, is a relaxed object that we can use as a test case. And for each of the clusters in our sample, we've assembled a data set which allows us to, for the first time in such a merger analysis, fully characterize the line of sight velocity structure for both the dark matter and the baryons, as well as the plane of sky morphology features for both the dark matter and the baryons. And so this is an example of one of each of those probes here for 4 different clusters in our sample, and I'm going to go much more in depth in each of those in the following slides. And so the really new bit of data that allows us to incorporate the line of sight ICM velocity into our analysis relies on us disentangling both the thermal and the kinetic Sunyaev-Zeldovich or SC effect. And so what we do is we take data from the ground-based Bolocam and Oztec instruments and combine that with Planck SC effect maps at 140 and 270 gigahertz. And we combine that with an X-ray derived temperature map from Chandra observations in order to disentangle the kinetic Sunyaev-Zeldovich effect from the data set, which allows us to then characterize the line of sight ICM velocity across the face of each cluster. And so this is an example of those line of sight ICM velocity maps for 3 clusters in the sample. And I do want to note that the uncertainties on these maps, though novel, are relatively large. And so Bolocam in particular has a PSF of about 70 arc seconds, and the uncertainties in each pixel are of order 1,000 kilometers per second. And so it's not super high resolution, and at the end, if we have time, I can go into what observations we're thinking about getting next in order to improve that. But once we've characterized the line of sight ICM velocity for all of these clusters, we get to work characterizing the line of sight dark matter velocity. And in order to do this, we first assume that cluster member galaxy velocities trace the dark matter velocity structure. And for mergers, this is a pretty good assumption. And so we use the DMOS and LRIS spectrographs on Keck to obtain cluster member galaxy spectroscopic redshifts, which we convert to line of sight velocities across the face of each cluster. Once we have that sample of cluster member galaxy velocities, we bin them up using a weighted Voronoi tessellation to create 2-dimensional maps like this. So in the top right-hand corner, I just wanted to point out this velocity map is the highest sort of resolution map that we have. This is of the quadruple merger MAX J0717, and we've got between 200 and 300 galaxies across the face of this cluster. So most of the galaxies have maps that look like the bottom 2 down here in terms of resolution. So once we've characterized both of the velocity observables, we can start looking at the plane of sky morphology. And so we actually have 3 probes of the plane of sky ICM morphology. So the first 2 come from Chandra observations of every cluster. We first generate an 0.5 to 7 keV X-ray surface brightness map, and you can see an example of that in the top right for MAX J0717. And then we also generate a contour binned temperature map for each cluster, so the top left figure here. And then finally, we have maps of the projected line of sight ICM density that we get from the thermal SC effect analysis here. And then finally, to characterize the plane of sky dark matter morphology, we use a strong gravitational lensing total mass reconstruction for each cluster in the sample. And so in order to get this, we use the light traces mass, or LTM approach, applied to multi-band HST imaging data. And so an example of this is shown in the bottom right. So once we've done this for all the clusters in the sample, we wanted to test our analysis pipeline out on one cluster. So we started with max data below 18, and this is the observational data set that we have for this cluster. And so there's a couple important things that I really want to point out here. Firstly is that in the top right, the total mass reconstruction, you can see 2 resolved total mass peaks associated with the primary and secondary cluster. The X-ray observables are quite interesting. So in the surface brightness map, we see this extended diffuse emission, and it's lacking 2 clear emission peaks associated with those cluster cores. The X-ray derived temperature map is very centrally peaked. And then in the 2 velocity observables, you can see that you can roughly by eye draw a dipole between each of those. And if you look at the upper map and compare it with the bottom map, you can see that the dipoles between those 2 velocity structures are not aligned. And so these are the sorts of observables that we want to be able to reproduce with our set of simulations in order to infer the initial conditions of the merger. And in order to do that, we start running some simulations using the Gamer2 code. And so we initialize these as very simple, idealized hydrodynamical binary galaxy cluster mergers. And so there's a set of initial parameters that are important here. We initialize each simulation with a value of the total mass of the primary and the secondary, along with the mass ratio in between the 2. The impact parameter is defined to be in the y-axis in this diagram here, and I promise that's important later. And then we offset the primary and the secondary cluster by a distance which is about equal to the sum of their virial radii, about 3 megaparsecs, and we assign them a relative infall velocity. And this initialization is good for visualizing in 3D space. And I wanted to point out that whenever I discuss projections that we make of these simulations, there's going to be what's called a viewing angle, which is defined by this vector L here. So the vector defines the plane in which we project observables to compare them to the observed data. So once we've initialized the simulations, we evolve them as a function of time, and we read them out at a series of epochs. So at each of these epochs, we generate a snapshot of figures, and each of these figures is a mock observable that we would like to directly compare to the observed data sets. And so we use YT to project most of these observables into 2D images. And then we additionally actually simulate X-ray event files in order to obtain the contour bin temperature maps for comparison to the observed temperature map. And for each of these observables, we degrade the quality of all of these mocks in order to create the most apples-to-apples comparisons as we can to the observational data. Then, in order to determine whether or not a given snapshot produces observables which are in good agreement with the observational data, so whether or not they actually reflect something similar to what we see in max data below 18, we apply a set of empirically calibrated matching criteria to each mock at each simulation. And I'm not going to go too in-depth into each of these empirically calibrated matching criteria because I only have 20 minutes and I have some interesting results I want to discuss instead, but you're welcome to ask questions about any of those at the end. So to gain a better intuition for how these simulations evolve as a function of time, I thought I'd include a movie here. And so these are simulation snapshots over a series of epochs for a simulation which produced some snapshots that were in good agreement with the observational data. And so I'm going to play this. I'm going to start at about a giga-year prior to the paracenter passage. And if you keep an eye on that tick mark in the upper right-hand corner, it'll indicate whether or not a given time step produces snapshots that are in good agreement with the max data below 18 data. So as we watch this evolve, we can start to see immediately that around the paracenter passage, we see some X-ray morphologies which are in agreement with max data below 18. So the X-ray surface brightness map starts becoming very diffuse and extended. I'll play this again. And you can start to see the temperature map heat up. In addition, if you watch the 2 velocity observables on top, you can start to see this induced rotation between the 2 dipoles that you can see by eye as we approach and as we proceed past the paracenter passage. So another way of looking at this is to plot all of the observables as a function of time for 5 different snapshots shown here. So each column here is a given time step in a simulation, and each row reflects each of the observables that we're comparing to the max data below 18 data. And in the top right-hand corner of each of these observables, I've indicated whether or not that given observable passes its associated matching criterion. And so you can see that if you look at, for example, the X-ray observables, they produce snapshots which are good reflections of the observed data at and after the pericenter passage. The 2 velocity observables indicate that only within a short range post-pericenter passage do you agree on what the velocity magnitudes for the ICM and the dark matter should be in terms of magnitude and orientation. Only around the pericenter passage do your total mass reconstruction lens peaks agree with the distance between that observed and max data below 18, and the optical depth map generally agrees with all of the observables. So that's nice in terms of pictures, but we can actually start to look at some distributions of these parameters. So we ran 2 sets of simulations in order to match max data below 18's observables. The first, we started with initial guesses for things like the mass ratio, the impact parameter, and the initial relative velocity. And what we varied were the gas distributions of the primary and the secondary clusters. And so I've plotted here distributions in the left-hand side of simulations which were initialized with various combinations of gas profiles. And you can see that for this last set of gas profiles which were tested, and so this is an intermediately disturbed primary gas profile and a strongly disturbed secondary gas profile, the highest number of simulated snapshots produced snapshots which were in good agreement with the max data below 18 data. And so this indicates that for all subsequent simulation runs, we should be using these 2 gas profiles, and so that's what we do. In addition here, I'm also plotting distributions of the epochs and the viewing angles, which were associated with these simulated snapshots. And so you can see that the epoch distribution is pretty well centered shortly after the pericenter passage, and that there's a clear preference for viewing angles which are offset from the merger axis, or the axis along which the velocities were initialized, by about 20 degrees or so. And so once we've determined what these gas profiles should be, we started varying the other initial conditions. So the mass ratio, the impact parameter, and the initial relative velocity. And the associated distributions are shown here as well. And so you can see that we're actually able to fairly well constrain the mass ratio between the primary and the secondary to within about 1.5 to 3. We're able to set an upper limit on the impact parameter at about 250 kiloparsecs. And the initial velocity of the 2 subclusters when they're separated by about 3 megaparsecs is somewhere between about 1,700 and 3,000 kilometers per second. We can also collapse these distributions of epochs and viewing angles which pass the matching criteria. And you can see we're actually able to constrain the epoch of the merger to within several tens of megayears post-pericenter passage. And we're able to quantitatively constrain the viewing angle to within about 25 to 35 degrees of the merger axis. And while all of these quantitative results on the initial conditions of the merger are very interesting, the thing that I wanted to spend a little bit more time talking about was this velocity decoupling that we're seeing between the dark matter and the ICM velocity dipoles. So here I'm showing several different pairs of velocity dipoles. So on the top is the ICM or the gas velocity dipole, and on the bottom is the galaxy or the dark matter velocity dipole. And as you start on the left, the viewing angle for those snapshots is looking straight down the merger axis. And then as we move to the right, we're stepping farther and farther away from that merger axis. And as that happens, we start to see this induced rotation due to the geometry of these 2 dipoles. And a really easy way to visualize this is with a simple 2D schematic. So you can imagine that as you approach the pericenter passage of a cluster merger, the DM and the ICM initially start well aligned, and then as you approach pericenter, the ICM starts to lag behind the dark matter. Due to its collisionality, it experiences things like ram pressure. And if you're looking down the axis of the merger, those 2 dipoles are going to appear very well aligned, even given the spatial offset between the dark matter and the ICM, because you're looking down that axis. But if you stay in that same 2D plane and you rotate away from the merger axis by, say, about 45 or so degrees, you can see that you can actually induce a flip in the sign between the dark matter and the ICM velocity dipoles. And so building on that a little bit more, this velocity decoupling is not only dependent on the viewing angle, but also the merger epoch, and this is very intuitive. So I'm plotting here the rotational offset between the dark matter and the ICM velocity dipoles as a function of viewing angle for 3 different epochs. So you can see that prior to paracenter passage, these 2 velocity dipoles are pretty well aligned for all viewing angles. But as you approach the paracenter, you start to see this induced rotation as a function of viewing angle. And in particular, if you recall the initialization diagram that I showed you earlier about the simulations, you can see that the more of the viewing angle vector that you take away from the merger axis and put into the axis of the impact parameter initialization, the more induced rotation you see. And then fairly intuitively, post-paracenter, as you move farther away from the merger axis, there's a general trend towards anti-alignment for all viewing angles. And then, just for fun, in order to gain a little bit more intuition for this, I'm going to share another movie. So the leftmost column here is going to be on top the total mass density, and the bottom is the gas mass density. And I've indicated the total density peaks with little stars in all of the plots here. In the middle, we're going to watch the X-ray derived temperature, and then the 2 velocities are on the bottom in the middle, the gas velocity along the line of sight, and in the top, the particle velocity or the dark matter velocity. And as we evolve this as a function of time, you can see that as we approach paracenter, there's this rapid rotation in the dark matter velocity dipole, which is lagged by the gas velocity dipole on small scales. And it takes several additional tenths of gigayears post-paracenter, I'll play this again, for those velocity dipoles to catch up to the dark matter velocity dipole on small scales, and even longer for those motions to propagate outwards towards larger radii. And so this is why we see this sort of continuous sampling of rotational offsets for instance, large impact parameters in these simulations. And so this is a very predictable phenomenon. So I just wanted to show here the sort of quantitative simultaneous constraints that we were able to make on these various merger parameters. And this is, to our knowledge, the first time in such a merger study that we're able to provide constraints like these. And then, in summary, there are several updates that we'd like to make to the ICM-SHOX pipeline. They're listed here, and I'm happy to chat about any of them. But in summary, we really do want to apply this updated ICM-SHOX pipeline to the full sample. So we've learned a lot of lessons in our application to Max Data 018. We've made a really cool discovery of the behavior of a velocity dipole decoupling between the gas and the dark matter. But once we then apply this pipeline to the full sample, we hope to obtain a set of observationally derived population statistics with which we might be able to test some cosmological models. So I'll leave it there.
Thanks, Emily. Really nice talk. Any questions?
Thank you. I really enjoyed the talk. I'm wondering if you could say something about when you talk about moderately or intermediately disturbed and very disturbed like gas profile. What does that actually mean in terms of what you initialize?
Yeah. So for the gas profile, we use a modified beta profile or the Vic-Linen profile. And what we've done is we've played around with a couple of those parameters, particularly the inner parameters shown here. And what we do is we define 3 sets of those parameters, which basically span this whole space of entropy profile distributions in the accept cluster sample. And so we contextualize them such that our cool core profile spans the lower end of this observed distribution. The non-cool core, the highly disturbed profile, spans the upper bit, and the intermediate profile kind of jumps between the 2 modes of this distribution here. So we tried to contextualize them with the best observational sample that we have available.
Any other questions? Come on, don't be shy. Well,
Nice talk. Well, this is just curiosity. So, are you thinking on also checking, the radio band?
Yeah. So we have thought about that a fair bit. And in this first application to MaxJ0018, we had some prior intuition that this merger was likely occurring along the line of sight, which means if there were radio relics, they wouldn't be super obvious, right? You see radio relics more when you have a plane of sky merger. And so we didn't actually use any of those constraints in this study, but it's something that we've been thinking about a little bit. So as we start to analyze, the plane of sky mergers, we might look into the radio band and see if the relics can tell us anything interesting.
Excellent. Okay, any other question? If not, let's thanks our speaker again. And Ellie will be here for the rest of the year, so feel free to go and chat with her. And okay, that's it.